These are a few steps that we can use when graphing rational functions. It's important to note that when we check for holes, that we need to make sure that whatever factor our hole has cancels completely. Also, when we find the attributes, always check to determine if it's going to cross, if our function is going to cross the horizontal asymptote, or if we have a slant asymptote, if it's going to cross that. A sign chart is a good idea because it helps us to see where the pieces should be when we graph it. And of course, let's go ahead and graph. So let's look at a couple more examples and see how we can do these things. The first thing that we want to do here is to factor completely. Notice that the numerator already has x plus 1, and we can't break that down any further. But for the denominator, we can do a little bit of work. So there are 4 terms here. Let's say that we tried to factor this by grouping. So if we group the first 2, group the next 2 terms, the greatest common factor in the first term is going to be x squared, and then we have x plus 3 remaining. In the second group, we can factor out a negative 2, and that's going to give us 3x plus 4. You'll notice that we can't go any further with this because what we have inside these parentheses is different from what's in the other set of parentheses. So factoring by grouping won't work here. Another method that we can use is a combination of the rational root theorem, the factor theorem, and the remainder theorem. And basically all that means is that we can take some values p and q as possibilities of what we can use in synthetic division. So the numbers for p are going to come from the last term, our constant term, which is this 8. So if we factor out this 8, and this is basically the rational root theorem that we're using here. If we factor out 8, 8 can be a positive 1 or it can be a negative 1 as a factor, or it can have a positive 2 as a factor, or 8 can have a positive 4 as a factor, or 8 can have a positive 8 as a factor. So those are all the possibilities of what we could use if we wanted to factor 8. We notice that the numerator here is 1, and the only factors of 1 would just be 1. So let's say we call this last set of numbers p and the first set q. Then the rational root theorem says that if we have rational roots, things that we can use in synthetic division, that it would be p over q. That would represent all the possibilities of what we could have. So if we did that, we'd have 1 over 1, positive or negative, 2 over 1, 4 over 1, or 8 over 1. In other words, our only possibilities of what we could try in synthetic division, if we have rational roots, are either positive or negative 1, positive or negative 2, positive or negative 4, or positive or negative 8. Let's say that we picked one of these to use with synthetic division, maybe 2. So we're going to use 2 here. So our numbers, we have a 1, a 3, negative 6, and negative 8. So we're going to use those coefficients, 1, 3, negative 6, and negative 8. So we can drop the 1. 2 times 1 is 2. Add 2 plus 3, that's 5. Multiply 5 times 2, that's 10. Add 10 and negative 6, that's 4. Multiply 2 and 4, that's 8. Add 8 and negative 8, we get 0. So looks like our remainder is 0. According to both our remainder theorem and factor theorem, we know that 2 is going to be a root. And if 2 is a root, according to the factor theorem, that means x minus 2 is a factor. So in other words, what we found out was this 2 represents x minus 2, one of the factors, and the other factor is this depressed polynomial that we have down here. Remember that we started with a power of 3 here for 1x cubed. Then we had a power of 2 here for 3x squared. And we had a power of 1 here for negative 6x. And our constant term, there was no x, that was a power of 0. When we divide, when we get our depressed polynomial, everything goes down by a degree of 1 or a power of 1. So this power of 3 up here is going to drop down and become a power of 2. So this 1 is really 1x squared. So x squared is what we're going to write. And this 5, if we drop this power by 1, would become 5x. And this 1, drop that by 1, that means that that 4 at the end is a constant. So we've basically started on to factoring the denominator. Now let's clean this up a little bit. So we found out that that denominator, x cubed plus 3x squared minus 6x minus 8, is going to factor as x minus 2 times x squared plus 5x plus 4. Of course, this part right here, we could use a normal factoring technique to factor that a little bit more. And if we do that, we would end up with x plus 1 and x plus 4. So in other words, this part here factors as what we have here. So now let's use what we know. We know now that the factored form, the fully factored form, is x plus 1 over x minus 2 times x plus 1 times x plus 4. Because of that, we know that there's a whole because these factors are going to cancel out. And when they do, they divide out and leave 1. So a number divided by itself is 1. So our simplified form is just going to end up being 1 over x minus 2 times x plus 4. But again, x plus 1 was where everything canceled out. That means that the root of this, of course, is negative 1. That means that at the root, there's a hole. So for x plus 1, there's a hole. So there's going to be a hole where x is negative 1. To figure out what that y value of the hole is going to be, we can take that negative 1 and substitute it back into the x's that we have here. And you can try it out yourself, but if you put negative 1 in for each of those x's, you're going to end up with negative 1/9 for your hole. Let's see if we can find some of the other attributes. So for the x-intercept, it's going to be anything that's going to make the y value equal 0. And remember that for a fraction, the only way that the y value will be 0 is if the numerator of our fraction is equal to 0. So what will make this numerator equal 0? Nothing, because it's just 1 forever. So there is no x-intercept. What about the y-intercept? To get the y-intercept, we're going to make all the x's equal to 0. So if we change these x's to 0 and work it out, what would we end up having? Well, we would end up with 0, negative 1/8. We next need to find our asymptotes. The vertical asymptote is going to be anything left over that's going to make our denominator equal to 0. So notice that if we take this x minus 2 and ask, what will make x minus 2 0? That's going to happen anytime that x is equal to 2. Similarly, for this next factor, x plus 4, if x is equal to a negative 4, then we're going to have 0 in the denominator. So again, for our vertical asymptote, we're going to make sure to check for values that make our denominator equal to 0. For our horizontal asymptote, we can either look at the original function or the factored form. Oftentimes, it's best to look at the unfactored form, the original function, to determine what the horizontal asymptote is. So if we notice here, the leading term here is 1x, and the leading term here is 1x cubed. So the denominator has a larger power, so a power of 3 versus a power of 1. So because it's bigger on bottom, we know that 0 is our y asymptote, so our horizontal asymptote. So our horizontal asymptote is going to be y equals 0. We should check if it crosses, but remember that we're going to check by setting the function, the original function, equal to what we have. But the original function simplifies down to what we have here. And will this function ever equal to 0? No. So we already know that it will not cross the horizontal asymptote. So now the third step that we're going to do is to come up with our sign chart. On our sign chart, we're going to put anything that is an x-intercept or anything that's a vertical asymptote so that we can create our graph. So our x-intercepts, we don't have any. Our vertical asymptote, we said we're at -4 and +2. So at -4 and +2, we're going to have vertical asymptotes. Let's say we chose some test values. To the left of -4, we might test out maybe -5. Between -4 and 2, maybe we can test out 0. And to the right of 2, maybe we can test out 3. So if we tested these out, in other words, if we put these in for x, what would happen? So again, test it out yourself, but if you put -5 in for your x values, for all your x values, you end up with a positive number. If you put 0 in for all of your x values, you end up with a negative value. If you put 3 in for all of your x values, you end up with a positive number. So this is enough information for us now to start sketching our graph. So first, let's put in the asymptotes. We have an asymptote, a vertical asymptote at -4. So here's -4. And we're going to go ahead and put our vertical asymptote in. We also have a vertical asymptote, we said, at 2. So here's 2. So if we put our vertical asymptote here, then this is what we have. So we also said that we have a y-intercept at 0, -1/8. So that point would be down here if we graphed it. We also said that we would have a horizontal asymptote at y equals 0. So here's our horizontal asymptote through y equals 0, basically through the x-axis. And excuse the messiness, it's kind of hard to draw this on a straight line here. But anyway, there's our horizontal asymptote through y equals 0, or the x-axis. So let's use our sign chart to see how everything goes. And keeping in mind, we already said that it will not cross the horizontal asymptote. So we know that to the left of -4, To the left of -4, we're going to have a positive value. To the right of -4, we're going to have a negative value. To the left of -2, we're going to have a negative value. And to the right of +2, excuse me, meant to say +2. To the right of +2, we're going to have a positive value. We know that this point, and this point, they're all a part of the graph. So we have to connect them. We know that this piece is a part of the graph and that it has to end up coming down to meet some other points below. We know that it's going to get closer to this asymptote, but we will not cross it. We've already verified that through our work. Similarly, on this side, it's going to get very close to our horizontal asymptote, but it will not cross it. So this is what our graph looks like. On this particular question, we already have everything completely factored, but notice that some of this is going to end up canceling out. So our x plus 3 and x plus 3 here is going to cancel out, which means, of course, that at x plus 3, for this particular factor, we're going to end up with a whole. So our whole is going to have an x value of -3 because that's the root of x plus 3. To figure out the y value of the whole, we're going to put this -3 back in for all the x values. So if we did that, we'd have -3 plus 2 over -3 plus 1 times -3 minus 2. And if we work this out, you can check it yourself, we're going to end up with -1/10. So let's see if we can find some of these other attributes. For our x-intercept, we're asking the question, what would make the numerator equal to 0? In other words, what's going to turn our whole fraction to 0, or make our whole fraction have a value of 0? And we know that that would only happen when x is equal to -2. That's the only thing that would make the numerator equal to 0. Of course, we want to write this as an ordered pair. So that would be -2, 0 for our x-intercept. For our y-intercept, we're trying to find out what happens when we set all the x's equal to 0. So in other words, 0 plus 2, 0 plus 1, 0 minus 2, and we worked everything out. What we would end up with is our y-intercept being 0, -1. So we get back -1 when we worked everything out. Let's see if we can find the other information. So far, we said that we have a whole at -3, -1/10. We said that we have an x-intercept at -2. And that was because these canceled out. -2 is the only thing that would make our numerator equal to 0. We also said that our y-intercept, in other words, when we change all the x's to 0, for our y-intercept, we end up getting back a -1. So 0, -1 is our y-intercept. If we look at our simplified fraction, in other words, that x plus 2 over x plus 1 times x minus 2, remember that our vertical asymptote is going to be anything that will make that remaining denominator equal to 0. So what values would do that? Well, x equals -1 would make the denominator 0. Also, x equals +2 would do that as well. We can also try to find our horizontal asymptote. But what we need to know here is the degree of the numerator and the degree of the denominator. If we look at our canceled terms, we know that the leading term in the numerator would just be x. The leading term in the denominator, we would get that from multiplying x times x. So If we only looked at the leading term, we'd have x to the 1 in the numerator and x to the second in the denominator, meaning that we have a larger degree in the denominator. In other words, it's bigger on the bottom, so y equals 0 would be our horizontal asymptote. Whenever we find the horizontal asymptote, we want to check if it crosses or not. And to determine if it crosses, we're going to set our horizontal asymptote number equal to our function. And we want to check to see if they're going to be equal to each other at a particular x value. So if we did that, we have x plus 2 over x plus 1 times x minus 2. We set that equal to 0 and find out if there are any x values that would make this true. So the only way for this fraction to equal 0 is if the numerator is equal to 0. So what values of x would turn that numerator equal to 0? Well, x would have to be a negative 2. So if x is negative 2, then it will cross. So it will cross, and it's going to cross wherever our x value is negative 2. But remember, at our horizontal asymptote, where it's crossing is 0. So it's going to cross at that point negative 2, 0. So the final thing that we would need to do, of course, is our sign chart. So our sign chart would have any x-intercept values as well as our vertical asymptote numbers. So on our sign chart, we're going to put negative 2, which is our x-intercept, negative 1, which is a vertical asymptote, and also positive 2, which is another vertical asymptote. We can choose some test values. So let's say we chose negative 4 as an example. And keep in mind, we can't choose negative 3 because there's a hole at negative 3. So we chose negative 4. Let's say that between negative 1 and negative 2, we choose negative 1.5. And let's say we chose 0 for the numbers between negative 1 and 2 to test those out. And we chose 3 to test out the numbers to the right of 2. It turns out if you input negative 4 in for all the x values, you end up with a negative number. If you input negative 1.5 in for all your x values, you end up with a positive number. If you input 0 for all your test values, you end up with a negative number. And if you input 3, you end up with a positive number. This is now enough for us to put our graph together. So when we start off, we can start really with any of the attributes, but let's say that we wanted to start with the x-intercept this time. So our x-intercept is at negative 2, 0. So right here. Our y-intercept is at 0, negative 1. So right here. Next, our vertical asymptote is at x equals negative 1. So negative 1, we're going to put a vertical asymptote through negative 1. And also a vertical asymptote through positive 2, where x is positive 2. We know as well that we have a horizontal asymptote at y equals 0. That's basically the x-axis. So where y is equal to 0, we're going to put our horizontal asymptote and notice that we said that it would cross at x equals negative 2. So it's going to cross right here. So let's use our sign chart to figure out how everything goes. So to the left of -2, we're going to have negative values. We'll get to that later. To the right of -2, we're going to have positive values. So over here, basically between -2 and -1, we'll have positive values. To the right, to the left, no, to the right of -1, we're going to have negative values. So we're going to have negative values here. To the left of 2, we're also going to have negative values. So we'll have negative values here. To the right of 2, we're going to have positive values. So we're going to have positive values here. We know there's only one place that we cross the horizontal asymptote. So let's put it together. So this point and our horizontal asymptote cross are going to connect. We said that we have to cross the horizontal asymptote, so we're going to cross it. Now notice that we have negative values down here, but we have to stay close to our horizontal asymptote since, as we discussed before, the horizontal asymptote represents the end behavior. So now let's connect the rest of what we have. So this point here, and this point here, they all have to be connected. And notice what we said about what happens between -1 and +2. So between -1 and +2, we only have negative values. And that's what our graph says here, that between those values, everything is under the graph. In other words, everything is negative. If we look at the values to the right of 3, everything is positive. And so keeping in mind that we will not cross our horizontal asymptote, we're just going to keep getting closer and closer, and that's what it looks like. One thing I'm missing on this graph, though, is the hole. So remember, we said that there's a hole at -3, -1/10. So when we get to where x is -3, there should be a hole. And I should have drawn it a little bit further down, but basically there's a hole right there where x is -3. So here we have another polynomial that is already factored, so no need to do the first step, but we can still check for holes. Notice that the x -3 is going to completely cancel out. So that means that considering that factor, x -3, that's going to tell us that there's a hole for the root there. So there's a hole at +3. To figure out what the hole's y value is going to be, we're going to substitute that 3 back into the in the simplified version of our answer. So we put the hole back in for each of the x's. We have 3 + 4 over 3 + 4 squared. If we worked everything out here, we would end up with 1/7. So there's a hole at 3, 1/7. But technically, we're not done canceling, because if we notice that we have x + 4 in the numerator and x + 4 squared in the denominator, let's say if we wrote that out a little bit further. So we said x + 4 in the numerator and x + 4 squared, in other words, x + 4 times x + 4 in the denominator. Notice that the x + 4 would cancel out, but you still have an x + 4 left over in the denominator. So in other words, everything would cancel out and simplify to 1 over x + 4. So remember, we only have holes where everything cancels out completely. So even though we had x + 4 cancel out here and x + 4 cancel out here, we're still left with x + 4 here. So since we still have something left over, we cannot say that there's a hole for this particular factor. Instead, what we can say is that this particular factor would tell us something about the vertical asymptote. So what we know from this is that our vertical asymptote would have to be at x equals -4. Let's say we found our other values. Since we're talking about asymptotes, let's say we want to find out what the horizontal asymptote is. So the horizontal asymptote here, notice that the denominator has a larger value, excuse me, the denominator has a larger value in terms of degree compared to the numerator. So the numerator is degree 0, whereas the denominator is degree 1. There is no x in the numerator, but the x in the denominator has a power of 1. So since it's bigger on the bottom, we know that y equals 0 would be our horizontal asymptote. And please excuse the pauses. I'm really tired right now trying to put this video together, but hopefully you guys get something out of it. So we have the vertical asymptote, the horizontal asymptote, and so now what we want to do is we want to check if it will cross. Always check if it crosses the horizontal asymptote. Or if you end up with a slant asymptote, always check if it crosses the slant asymptote. So again, will it cross? Well, we only know that if we take the function and set it equal to what the horizontal asymptote's number is. So will this ever be true? No, because the numerator here is 1 forever. And there's no way to make this equal to 0. So this fraction will never equal 0. So will it cross? No. So no cross. What about the other attributes? Well, the x-intercept is found by, in the case of a rational number, asking, is there anything that's going to make the numerator equal to 0? So we already answered that question. Nothing's going to make that numerator equal 0. It's 1 forever. So there is no x-intercept. How about the y-intercept? Well, the y-intercept, we said we would have to make all the x's equal to 0. So if we did that, we'd have 1 over 0 plus 4, basically 1/4. So our y-intercept would be 0, 1/4. Let's clean this up, write down our attributes, and see if we can put this together for our graph. Well, of course, after we do our sign chart. So we found out just now that in terms of x-intercepts, this function has none. We said also that the y-intercept was at 0, 1/4. We noted as well that the vertical asymptote was at x equals -4. We said that the horizontal asymptote was y equals 0 because the degree was bigger on the bottom. In terms of the horizontal asymptote crossing, we said that it will not cross the horizontal asymptote. Now let's do the sign chart. Remember, our simplified form for this particular rational number was 1 over x plus 4. So it's a lot easier to do the sign chart for that than the original function. So we're going to put anything that's an x-intercept or anything that's a vertical asymptote. There was no x-intercept, and the only vertical asymptote we had was -4. So -4 is the only number we're putting on the sign chart. Our test values, we can choose -5 because that's to the left of -4 on the number line, and 0 because 0 is to the right of -4 on the number line. If we substituted these values, what would happen? So we already know that if we put a 0 into our function, we got positive 1/4. So if we input 0, we're going to get a positive answer. If we put -5 in, well, think about it, 1 over -5 plus 4, that's going to give us a negative number. So now we're ready to do our graph. So on our graph, we can start with any of the attributes. Let's say that we wanted to start with the y-intercept. So the y-intercept is 0, 1/4, so maybe about here somewhere. We know that the vertical asymptote is at negative 1/4, excuse me, at negative 4. So at negative 4, we're going to have a vertical asymptote. Also, we know that we have a horizontal asymptote at 0, and we know again that it will not cross the horizontal asymptote. So this line will not get crossed. So let's put everything together and see if we can come up with the graph. So for our sign chart, we said that to the left of negative 4, that we'd have negative values. So we'd have values down here. To the right of negative 4, we have positive values. So we have values up here. We know that we will not cross the horizontal asymptote. And so when we start connecting our points and keep going, that we're just going to keep getting closer to our horizontal asymptote, but we will not cross. Also, we said that, didn't write it down here, but we said that we had found that there was a hole where x was negative 3, excuse me, positive 3, specifically at positive 3, comma 1, 7. So when we get to positive 3, we should have a hole there. Concerning the other part of the graph, we know that, again, we have to approach our horizontal asymptote and we will not cross it. So we're just going to get closer as we get to negative infinity. So here's a bonus example. And looks like, again, being tired, I typed this out wrong, but this should have been an x. You know, on all the examples that we've done prior to this, we have not had a slant asymptote. Remember that the slant asymptote is going to happen anytime the numerator is exactly 1 degree higher than the denominator. So the degree down here is 2, whereas the degree here is 1. So it's bigger on top. We know there's no horizontal asymptote, but because it's exactly 1 degree more in the numerator than it is in the denominator, that there is going to be a slant asymptote. So how do you find the slant asymptote? Well, we find the slant asymptote with division. So we're going to divide here. And because the degree down here is 1, looks like synthetic division would be a good choice. But how do you do synthetic division? There's nothing here. If it said plus 4, you'd put a negative 4 in the box here. If it said minus 2, you'd put a positive 2 inside of that box. Well, remember that x is the same as x plus 0. So why not use 0 in our box? So if we're doing synthetic division, we're going to use 0 here. We know that this x squared is really 1x squared. So for that power of 2, we have 1. We know we should drop a power each time, so we need to write a constant for the power of 1, also a constant for the power of 0. So in this case, there is no x, so we need a placeholder 0. For our power of 0, we know that that's going to be 4 because there's no x that goes with that 4. So if we did our synthetic division, drop the 1, multiply by 0, that's 0, add 0, that's 0, multiply by 0, that's 0, add 0 to 4, that's 4. So what exactly would be our slant asymptote? Well, we know we have a remainder of 4 here, but that's not the slant asymptote. The slant asymptote would come from everything else, from right here. So how would we express this? Well, it's just 1x. So in other words, our slant asymptote would be y equals x. So let's see if we can find everything else that we need here. So we said that our slant asymptote was at y equals x. And by the way, we cannot factor x squared plus 4. We could factor x squared minus 4, but as it stands, this is not factorable. So let's go ahead and find our attributes. So for the x-intercept, we would ask what would make the numerator 0? Notice that we're squaring, and anytime you square a number, it will be positive. For example, if I said negative 5 squared, that's a positive 25, or negative 3 squared, that's a positive 9. So anything I square will be positive, and if I add 4 to it, then it's even more positive. So this will never be 0. So our x-intercept, we're going to say that there is none. For our y-intercept, we would change all the x's to 0. But if we did that, what we'd end up with is 0 squared plus 4 over 0. In other words, we'd end up with 4 over 0 that is undefined. So we can't have this. So the only solution we can have here is to say that we don't have a y-intercept. This will never be allowed, us inputting 0 for x. Well, what about our horizontal asymptote? Remember, if we have a slant asymptote, we can't have a horizontal asymptote, so there's none here. Again, it was bigger on top, so there is no slant asymptote. What about the rest of what we need to do? Well, at this point, we said that if we have a horizontal asymptote or a slant asymptote, we should check if it crosses or not. How do we do that? We set the value equal to the function. In this case, the value of our slant asymptote is just x. So to check if it crosses, we're going to set our function equal to our slant asymptote and see if we can do our algebra to get an x by itself. So in this case, to get rid of the denominator, we can multiply by x. So the denominators are gone. Excuse me, the denominator is gone. And we're just left with x squared plus 4 on the left. And on the right, we have x squared. If we subtracted x squared from both sides, what would happen? Well, on the left, they would cancel out. We just have 4. And on the right, we just end up with 0. So is this true? Can 0 ever equal 4? No. So what we're going to say is that since this is impossible, we will not cross our slant asymptote. The only other thing for us to do is to do our sign chart and put our graph together. But again, let's clean this up and recap. So we said that for our x-intercept, that we had none. For our y-intercept, we also had none. For our horizontal asymptote, since it's bigger on top, there was none. For our slant asymptote, we got y equals x. And so we need to figure out, the only other thing we need is our vertical asymptote. So our vertical asymptote is whatever would make the denominator 0. So what would make the denominator 0? That would happen only if x is equal to 0. That's all we have in the denominator. So let's do our sign chart. And by the way, we said that we checked if the slant asymptote, if it crossed the slant asymptote, we said it did not cross. So on our sign chart, the only thing that we're going to put is either an x-intercept or a vertical asymptote. So we have no x-intercept, so our vertical asymptote, the only number we had was 0. So for our sign chart, we're going to choose a number to the right of 0, maybe 1, and to the left of 0, maybe -1, and we're going to use those to test everything out. If we input -1 in for all the x's, then we would end up with a negative number. If we input +1 in for all the x's, we end up with a positive number. So now let's put everything together and make our graph. So we know that our slant asymptote is the line y equals x. So we have to remember a little bit of algebra 1 to graph it. So y equals mx plus b, the m is the slope and the b is the y-intercept. If we have the line y equals x, the slope is 1 and the y-intercept is 0. So we're going to start off at 0, go up 1, right 1, up 1, right 1, and we'll keep going to be able to make our slant asymptote. So we're just graphing the line y equals x. And of course, we can reverse that to get the other part of our graph. So we've graphed the slant asymptote. We know that for our vertical asymptote, that x is equal to 0. So our vertical asymptote is going to be like this. On our sign chart, we said that to the left of 0, everything's going to be negative. So to the left of 0, we have a negative value. To the right of 0, we have a positive value. And we said that we will never cross our slant asymptote. We checked that up here. So what that means is that when this comes down and stays close to our vertical asymptote, it has to come back around and stay close to our slant asymptote, and it will not cross, but it will just keep getting closer. Similarly, on this piece right here, it's going to stay close to our vertical asymptote and our slant asymptote, but it won't cross. It's just going to keep getting closer to our slant asymptote. So this is what our graph would look like.